Okay, so here we are. So sorry about the delay. So today, lecture 8. As a reminder, last week we talked about exploratory factor analysis, and leading on to that, I already mentioned last time there's a difference between exploratory factor analysis and confirmatory factor analysis. And so leading to that today, we'll do a confirmatory factor analysis by structured equation models. And then next week we'll return back to mediation. So it's a little bit perhaps of a weird structure, but it's I thought it would be more sensible to have exploratory and confirmatory right behind each other, where I introduce you to structured equation models, and then we go back to doing mediation, but then via structured equation models, and perhaps also combine a bit of both. So you can have confirmatory factor analysis combined with mediation analysis in case you want that. So that's the goal for today. I'm going to talk to you about Latent and CFA SEM, so confirmatory factor analysis SEM. I'm not going to be able to make you a SEM expert in just a single lecture. That would take an entire separate course. But you should be able to apply the basics, and you should understand what the purpose of it. And also, when you come across papers and structured equation models, it should help you with understanding what all those arrows mean and all those terminology means. So, did any of you ever come across structured equation models in your things? You've not read any things where people develop, for example, scales, and they use a structured equation model to validate scale, because, or they have a theoretical model which they're validating, where they build paths. No? Well, so they are quite common, and especially in the psychology of measurements, they are quite common, and that's also why you need to know a little bit about them. So some of you might go on to develop your own scales for measuring burnout, for measuring whatever, or you're trying to validate a scale which somebody else has used in a different population, or you're trying to see if it's the same across a group of patients and another group of patients to see if you're measuring the same thing. And that's why we use confirmatory factor analysis. So for the assignments, after today you should be able to complete the following sections for assignment 2. Not surprisingly, confirmatory factor analysis via SEM, which is a chunk in your things, and it also has a bit on measurement invariance, which we'll cover today. So last week we covered exploratory factor analysis. Factor analysis, as you remember, is used to find a set of unobserved hidden structures in your data. So the idea is that, for example, you might not be able to assess intelligence directly, but giving people lots of different tests, like Raven's progressive matrices, reaction time tests, all sorts of other tests, you might be able to capture this hidden construct or this latent construct that you're trying to get at. So you have latent variables or dimensions, as they're called, and then you have observed variables or manifest variables or indicators. So basically things you measured with your questionnaire. So the idea is that we have imperfect measurements. There's some type of hidden structure lurking underneath, like a personality trait or intelligence or something else like well-being, which we're unable to capture perfectly. But via our questionnaires, we're trying to approximate that, and we're trying to describe that hidden construct. Does everybody understand sort of the premise of this? Or yeah. So basically, we have. You can also think of it as we have a large number of questions, and we also want to reduce some of the complexity to it. So you might have 40 or 60 or 80 or 100 or 120 personality questions, and you're trying to reduce that to those six or 5 personality domains, or less if you believe there's less. And so think back to the personality example of last week, where we again in class we did this. So we had questions, and we saw the structure emerging. There's five factors in terms of personality, and we also did the same thing with the Sedanius data, with the teacher data, and we saw some constructs emerging in terms of something to do with confidence, something to do with approachability. So those hidden type of constructs we saw emerging. Why is this useful? Mostly it's used for questionnaire validation, and usually people have hypotheses or theories about how many dimensions there are to personality. So you might be arguing for 5 dimensions of personality, and then you might want to test that against a 6-factor model or 4-factor model or a 3-factor model. So it's in order to validate that. And also you want to, for example, this is quite interesting in terms of cross-cultural measurements. So suppose you make a measure for burnout, you might want to take it to different countries, and you might want to see if it's measuring the same thing in every single country. And so in order to do that, we also use structured equation models and confirmatory factor analysis. So we want to make sure that if if you're using a measure that it's measuring the same thing in every single country or in every single group, so if we're comparing men versus women, for example, or in every single group of patients. So if you have a burnout questionnaire and we're using it for people who are depressed, but also for people who are anxious, we want to make sure that it's measuring the same thing across all those different groups. And if it's not, we want to find out where it differs, and it might differ in interesting ways. So it also is quite useful, for example, to find out, as we also saw in factor analysis, sometimes you have items which don't do very well, which load very poorly on all hidden constructs, and then sometimes you might get rid of those factors. So you might gain something by simplifying. So you might start out with a large pool of items or a large pool of questions, and then you might filter through and find out those questions are not really able to discriminate between those personality traits or between those hidden structures in your data. Yeah? And so ultimately you would also be able to assign scores then. So as in the example, so you could assign a factor score, an extroversion score, and you might then use that later in discriminating between people on certain personality traits. So you might assign scores to every single question, but you might also be able to assign scores to every single participant. And you might then use that to predict certain outcomes or to use further in correlational analysis or in some other way. So last week we did exploratory factor analysis. As you might also remember from in class, there was quite some ambiguity. So we had 8 different ways of determining how many different factors there were. Some people came to slightly different conclusions as to how many factors there were than other people. There are some things like, does it really dip? Is it like you're really, so this type of screen plot, is it really that type of cutoff? And there's lots of ambiguous cutoffs, you would say, ambiguous decisions. You might be able to validate every single step along the way, but it's sort of, to some degree, there's a lot of gray areas in that aspect. To some degree, that's fine because it's exploratory, so you're just trying to find out what's going on. So you might not attach too much value to it, but ultimately we might want to have, it might be better to make explicit decisions. So I might say, we think there's 2 different theories. There's one which says there's one factor of personality. There's one which says there's 5 factors of personality. We're going to pit them against each other and see how well they do. You haven't missed too much. I'll just really briefly recap. So we've arrived at structural equation models, and today we're going to talk to you about confirmatory factor analysis, about exploratory factor analysis. And the purpose of that is usually validating questionnaires and reducing issues, so measurements. So you might have, let's say, 120 questions, and some of them might not be very good, and you might be able to remove some. And might also be able to help you discriminate between groups, or it might be able to validate measures across different groups. So you're trying to build a model for 5 personality factors, and you're going to try and test if that's the same structure in Zimbabwe as it is in Australia to see if people have the same personality dimensions across the globe. So it's useful for that as well. So as I was saying, the downside of exploratory factor analysis is that there's lots of ambiguous decisions, and with confirmatory factor analysis, you have to make a lot more explicit decisions. So it's you can still tinker a little bit and try to get away with things, but it's if you wanted to cheat, use exploratory factor analysis. For confirmatory factor analysis, it's a lot harder to cheat and say, oh, this. So you might be able to find one of those 8 things which sort of supports your thing and then slightly bend it that way. But it's really a lot harder to do that with confirmatory factor analysis. And usually it's especially helpful if you already have theories, for example, how burnout is measured, or how personality is measured, or how many dimensions there are to intelligence, etc., etc. So unfortunately, there's always more terms. So this is just to help you also when reading literature. So we have the observed variable, which is an indicator or manifest variable. It's something you measure. So it's basically one of your questionnaire scores, a 1 to 7 or 1 to 9 score of something you measured. So a questionnaire on happiness questionnaire, a question about personality, and usually by default it's denoted with a rectangle in your graphs and in your pictures. Then we have the latent variable. We assume that people's answers to the, things like a happiness questionnaire are being caused by an underlying hidden lurking construct like well-being or happiness or something else. And that's causing people to score high or low on our variables. And that's the latent variable, or construct, or unobserved variable, or dimension. That's what people tend to use. And that's denoted via an ellipse, an elliptical. And examples would be well-being, openness, intelligence, and it's denoted with a circle or an elliptical. So sometimes things vary, so they're not so there might be very high loadings between items, for example, or there might be loadings between different hidden latent constructs. So well-being might relate to also openness in some way. And in that case, we draw double-headed arrows between those constructs. And those basically signal covariances. Sometimes also people use correlations because their covariances can be converted into correlations. But basically, if things are allowed to vary together, then we use double-headed arrows. And then we have residuals. They're the trash bag. And mostly we report them in order to give people an estimate of like how much noise there's still going on, and we report the variance of that. So on those models, you'll usually see the variance of the residuals, and it's either denoted via an E for error term or an arrow with just a value on it. And so it's and sometimes it's also a double-headed arrow to the same thing. So sometimes people use a single arrow to the observed variable, but it's always to the observed variable. Sometimes, depending on which package you use, we'll have double-headed. I'll give you some examples. So Literal uses a single-headed arrow, and SEM and SEMplot, which we use, will use double-headed arrows. But it will become clear when we run through some examples. Yeah. So those are key components of these graphical type of models. How is it done? I don't have time to explain to you it in detail, but it's matrix algebra. So basically, everything is regression. The factor analysis from last week, also regression. Those regressions can be analyzed in a large matrix, and we can do matrix algebra in order to solve that matrix. And if we're unable to solve it, or there's multiple solutions to it, we can estimate what the values would be in that matrix. So we can rotate the matrix, we can calculate the eigenvalues of it, we can minimize or maximize the eigenvalues, and that's how it's done in terms of the computation behind it. So when you see that it does iterations trying to estimate something, it's basically rearranging our model into a series of equations, which we try to solve, and then that's what we get. So I won't go into any of that. Usually it's not also reported, that's the back end. It also means that in order to do structural equation modeling, you can also just feed it a matrix of correlations or a matrix of covariances, because it can use that to do the computations with. So it doesn't mean you have to have the raw data of, as you had before. If you find an article which has just a correlation matrix, you can use that. If you have a correlation matrix and the number of people it's measured from, you're able to reconstruct or build confirmatory factor models. Yeah, because it's all matrix algebra. Any questions? Suppose not an algebra, but so outside of R, there are many specific packages which will do structural equation models for you. And so this is also again a pitch as to like you might still not be fully convinced that's why we had abandoned SPSS for R. You might still feeling like I'm missing all sorts of pointy clicky things, and this is giving me lots of nasty errors, which SPSS doesn't do. But this is where you would have to leave SPSS anyway, because this doesn't happen in SPSS. SPSS has AMOS, which is an extension package to it, which allows you to draw these type of models, but you wouldn't be able to do any of this in SPSS. SAS can do some of it, but for SAS we'd also have to write code and structures like that. So there's many different packages which will do it, but again, R is free, open-ended, and you can, if things don't work, you can change it if you want to. Today we'll focus on Lavan, which is a structured equation model package. There's other packages like SEM, which is an older package which will do this. OpenMX, which is specifically developed for genetics and twin data, which will also do it, but I won't talk to you about any of those in detail, because most of the things you should be able to do with Lavan. Lavan stands for Latent Variable Analysis. It's developed by people in Ghent, and it's actively maintained, which is why I teach you Lavan rather than the other packages. So an example. So this is actually from the Latent type thing. So this is the type of model we're going to try and reconstruct. It's data on children's performances in 2 schools. And we have, it's called the Holzinger-Schweinfurt data from 1939. It's a classic structure equation modeling example. So you have 3 items measuring kids' visual performance, 3 items measuring kids' textual performance, and 3 items measuring kids' reaction speeds. And so the idea is that they're hidden constructs. They're things which the test psychologists went out and tested. And then those double-headed arrows are allowing for correlations between those 2. And what we haven't plotted here are all the residual errors on top of that. So the rectangles are the things which were measured. Those are the hidden constructs which we think are explaining the scores on their tests, and we're allowing them to co-vary. Yeah. And so a 3-factor model or 3-dimension model. So notice also that the arrows are going outwards. So it's sort of this is causing this. If you do a principal component analysis, the arrow will be pointing inwards. So that's the default notation. So you remember from last week, I talked to you about principal components analysis versus principal axis factoring and factor analysis, and that's also to do with how the logic of the arrows going in or out. So it's a subset from 2 schools, and this is what we're going to try and model, and then we're going to try and do some additional things with it, and then we start with some things. But first I have to tell you a little bit about notations in Latent. They're slightly different from your regular R notations, and some things you have to know. So F stands for factor, and so in this example, and so Y is F1. So this doesn't correspond to what you saw before. This is just showing you the notation. Yeah, and so the tilde, as you know by now is a function of our equation. So you will come across this with regression and GLM. So factor 1 here is a function of factor 2 and factor 3. So it's a higher order factor. Yeah. And so these would be the indicator variables or the observed variables that we had before, the ones that are measured. Yeah. So we can then write out those factors. Yeah. So we have something defining this, and then we define all those things. But factors are defined with is and then the tilde. So that's how Latent knows it's factor. Yeah. So this means regression equation. This means factor. Double tildes are for modeling variances and covariances. So this is the variance of itself. This is the covariance between I1 and Y2. And so you can also have covariance, as you saw, arrows, double-headed arrows going between those latent constructs. Yeah. So again, this is just notation. It will become clear once we do it. And then you can have also, we won't run into too much of this, you can have fixed intercepts. So sometimes you can fix things across models, and you can say this should stay the same and can't vary across both models, and that's how it's donated with the 1. And so in this case, this one is has a fixed intercept. This one has a fixed intercept. And usually that's for computational reasons. So sometimes we can't find a solution, but it works if we say this thing cannot vary, and then because it's a function of all the other things, you're able to do that. But we'll come across those things. For now, all you should know is that those are the type of notations which Latent uses. So our model here is a very simple model, and the nice thing is if you it has some sensible default, so it will by default draw all those double-headed arrows and will model all those variances, unless you explicitly tell it. If we had like x7 tilde tilde x7, then it will have removed all of the other things, because then it's assuming you're going to do something very specific or very explicit. But by default, it will model all the things. These 3 lines will model that. Yeah. So visual is so that's what we call our factor, and so that's the denotation for a factor: x1 plus x2 plus x3, textual, and then speed. Yeah. So that will give you that model. Now, fortunately, the beam resolution isn't all very good, but this is visual: x1, x2, x3, textual: x4, x5, x6, and speed: x7, x8, x9. So again, this is quite a very simple model. We only have 3 items loading on every factor, and we only have three hidden factors. We have no super factor. So we could have another factor here, for example, which we think explains everything further, which would be something like intelligence or performance or ability, which explains visual, textual, and speech. So we could have another hidden bubble here saying it's a super factor. Or we could combine all these three into one, and we'll come to that as an example where we have a one-factor model, so all 9 items loading on one thing. Yeah. Any questions so far? So now our model in Lavaan, in order to define the model, very important, we have to place it between single quotes, so not double quotes. And so if we think of this in our terminology, it's a list. Yeah. So and it will basically, what Lavaan will do is it will read it like a list and will look for things that resemble Lavaan code. So this is not a data frame. This is not a variable. It's a list. Yeah. So I set my working directory. I tell I need Lavaan. We don't really need it for this yet because this is just saying assigning a list to it something. And this is, I call this model 1. And you can annotate again with a hashtag things for yourself to remember, and then will be disregarded by the code. But yeah, be careful if you put in numbers or things like that, because then R might think it's variables and things like that. So don't have a number before the hashtag or something like that, because then it won't do it. So this is basically the model that you just saw written out in terms of equations. Yeah. So that's where structured equation models come from. It's basically a series of equations to describe a graphical model. Any questions? So before we go on and actually plot our model, something very important, which are assumptions. We have to consider several assumptions. One is we're dealing with regressions, and factor analysis are a variant of that. We talked about the assumptions for factor analysis, and by and large, what we saw last week applies this week as well. So if there's no meaningful correlations, for example, it doesn't make sense to do factor analysis. So if there are, that's what I just said. So one would basically first make a correlation matrix to see if there's something going on, and then proceed to do factor analysis. And one way is also to, again, use the KMO test, which we used last time, where we had meritorious and marvelous, as you might remember, to do that. And so here I've just done that for this. So I've called the site package, which does the KMO test. I've made a separate subset of the data frame. I've loaded the data from the Lavaan package. The data also has, we only want the 9 items. It also has some things on schools and the gender of the kids. And for the KMO test, we only need the 9 items. So column 7 to 15. And then this is KMO F data to do this. And then we see it's doing quite well. It's not doing great, but 0.75, it's enough to proceed. And there's something going on at least. If it was 0.3 or 0.4, we would worry, because that means there's not much correlations going on. And again, you can get it for every single item. And you can see, for example, that for X7, it is quite low. So there might be some issues there. Yeah. So the same as you would do with factor analysis, you would either examine a correlation matrix, or you would do a KMO type of test to see if it makes sense to proceed to do this. I also mentioned to you last time that data should be multivariate normal. Yeah. And this is not looking super great. You can sort of see it's veering off from the line. Yeah. So those are the type of things we've used before. So the nice thing is that, yeah, people don't tend to worry too much about it. There are ways to do robust estimations. Maximum likelihood. So if you do regular regressions, you would use ordinary least squares regression, and that's a single estimate. A maximum likelihood is a different way of estimating all the parameters. So what will happen is that the parameters are likely correct, but your standard errors are going to have issues, as you might be over or underestimating, and you might also be over or underestimating the fit of your model if this doesn't fully show multivariate normality. So we'll just proceed as if things were perfect, but you should bear in mind that things are not perfect, and there's ways to change in Lavaan, and I've put those in the exercises because they're more advanced. Not in your assignments, but in your exercises, to deal, for example, with robust ways of doing this. So things which don't require multivariate normality in order to still estimate it. And again, bootstrapping might alleviate some of those things. And when we talk about mediation, I'll show you how to do bootstrapping. So when we talk about mediation via SEM, I'll talk to you about bootstrapping and how we can alleviate some of those issues. In case you were wondering, so that's the actual printout from the Mardia test, so that was just a graph. So 0.045, so that's not good, and highly significant for skew, and the conclusion that they are not multivariate normal. Again, you have to bear in mind larger data sets will be more likely to exhibit non-variate normality, problems with multivariate normality, but that doesn't always mean it's very that big a deal. But you can see here is some veering off and some deviation, which isn't very good. So usually look at the graph first and see how bad it is. It's slightly better than the one we saw last time where it was really going off, but it's not great. Any questions? Okay, now to do the actual analysis. Again, I've just called Lavon again because R is forgetful. So in every single chunk, I will try and remember to call things. So fit CFA for confirmatory factor analysis. The model that we just described in that between those single quotes. Yeah. The data it has to use, and then what I did here is I made a sink because, as you might imagine, we might be getting massive output again. So I'm going to walk you through that output. It won't print all over here, so I'll open the text file. And so you can use sync to write away outputs to text files, which you can then examine rather than it printing all to your console. So let's have a look. So summary fit class. I'm not sure how readable it will be. I won't run you through all the things again, but this is the output you'll get. We had 301 kits basically in this analysis. The estimator by default was maximum likelihood, which I just mentioned to you. It has estimations. These guys, you remember, like the Tucker-Lewis index, you remember, and also you remember the RMSEA, you remember from last week. And then you might have also remembered some of the AIC, BEC type of measures we talked about last time. And so that's the output it prints. So these are the fit measures, a whole bunch of them, and we'll come to that in a bit as to what people actually report. And then we have the parameter estimates. So one of them, every single time it will constrain the first one to 1, because we can estimate what's going on, because 1 is just a function of the other one, so it will by default constrain one of them to be 1. And these are unstandardized estimates. Unless you say standardized is true, it will be unstandardized estimates. So, but you can have significance tests, so that's quite good. So they all seem to be loading on what there should be loading. Lots of them were not significant, then there's time to worry. So it means that the arrows we've drawn to that latent construct don't really map up. But this is the visual one, the textual one, the speed one, and this is the covariance. So those double-headed arrows we had going between speed, visual, and contextual. So those are estimated here, and again with significance tests. And these are the variances of our trash bag, so to speak, of those double-headed arrows going to the same thing. So basically things we don't explain, and lots of unexplained variance still, which is what you would expect. Yeah. So similar to the output you might have remembered from last time from the exploratory factor analysis, we have some loadings here and some significance tests. And you can work your way through it when you do the exercise and work through some further examples. So, back to this. Some familiar faces. So we saw the Tucker-Lewis index, and that showed an acceptable fit. You should remember that one was close to 1 was good. As did the CFI. The CFI is another fit measure which is also quite commonly reported in terms of structural equation models. However, the RMSEA, we wanted that to be below 0.05 ideally, 0.07, 0.08 still acceptable, but that's a relatively poor fit, with a confidence interval ranging from 0.071 to 0.114. So again, it's good in some aspects, but not good in some other aspects in terms of fit indices. So the CFI is another fit measure, which is commonly reported, which is why I reported it here. Depending on your supervisor, he or she will have specific preferences on what to report or what not to report. But we saw that there are many different fit measures there. But most commonly reported are the TLI, the CFI, and the RMSEA. Those are the most commonly reported. Some argue that you should have a CFI of higher than 0.95 if you're very conservative. And most of the time I would stick to reporting those three, RMSEA, CFI, TLI. And some of these things you saw before, except for the CFI, which we didn't cover in much detail last time. Okay, now we're going to try it yourself. So we're going to return to the model which we tested in class last time. You can click from downloads to do it there, and you can write a three-factor model in Lavance format and evaluate the fit measures. So basically, this should take you to download the one which we did in class, which was the Sidanius data, and then you would do a three-factor model. I'm not sure if you saved your output from last time, because otherwise it might be quite hard to reconstruct what the three factors were.